Swayam Prabha. Digital India. Educated India.
Welcome friends to this fourth lecture of week 6 of this online certification course of environmental soil chemistry, and in the previous 3 lectures we have talked about the different types of chemical kinetics and different order reactions. We have talked about some of the rate limiting transport process, and also we have defined what is the first order reaction, what is the second order reaction, and how first order reaction can be plotted, how second order reaction can be plotted, what is the difference between first order reaction as well as second order reaction, and how to calculate the half life of first order reaction, what is the formula of half life for the second order reaction. And today we are going to talk about zero order reaction and how we can actually apply these different order reaction to define different soil chemical processes and how to identify those. So, if we start today with the definition of the zero order reaction, in some reaction the rate is apparently independent of the reactant concentrations, and the rates of these zero order reactions do not vary with increasing nor decreasing reactant concentration. So, basically this is constant. So, in other words, the rate of this reaction is equal to the rate constant K of the reaction, and this property basically you can identify, you can see that this property differs from both first order reaction and second order reaction, where the rate constant is dependent on the reactant concentrations. So, again in the zero order reaction the rate is independent of the reactant concentration, it is constant, and so it does not depend on the decreasing reactant concentration or increasing reactant concentration. So, there are certain properties, there are certain conditions to fulfill zero order reaction. We are going to talk about that. Now, there are two general conditions that give rise to zero order rates. First of all, only a small fraction of the reactant molecules are in location or state in which they are able to react. So, very small fraction of the reactant molecules are generally go through this zero order reaction. So, they are able to react, and this fraction is continually replenished from the larger pools. So, only very small fraction of the reactant molecules are in location or state in which they are able to react, and this fraction is always continuously replenished from the larger pools. Second condition is when two or more reactants are involved, the concentration of some are much greater than those of others. So, if we consider there are two reactants, one is reactant A and reactant B. If we consider the concentration of reactant B is much greater than that of concentration of reactant A, then that could serve as a condition or as a as a condition or prerequisite for zero order reaction. Now, this situation you can commonly occur, you can see it is commonly occurs when a reaction is catalyzed by attachment to a solid surface, in case of heterogeneous catalysis, or to an enzyme. So, this type of reaction you can see in the catalysis as well as in case of enzyme, this type of zero order reaction mainly predominate. So, let us see what is a differential form of the zero order rate law. Now, you know from our definition from our previous lectures that for each each order reaction, be it a first order reaction or second order reaction, each of them can be defined in terms of differential rate as well as integral form. So, similarly, zero order reaction also can be expressed in terms of differential form as well as integrated form. Let us first discuss its differential form. So, in the differential form of zeroth order of law basically says, as it as indicated by its definition, the rate of the reaction, which is denoted by minus dA by dt, is equal to k and concentration of a to the power 0, which is basically k. So, which is a constant. So, here rate is equal to constant. So, this is a differential form of zeroth order reaction, where rate is the reaction rate and k is the reaction rate coefficient. Now, in this example, the unit of k is m by s, that means it is basically concentration versus concentration per time, unit of time. So, it is a molar per second, it could be mole per second. So, the unit can vary with other type of reaction, as you already know. In case of first order reaction, it is different. In case of second order reaction, it is different. In case of first order reaction, the rate constant is basically time inverse, whereas in case of second order reaction, the rate constant has the unit of concentration inverse into time inverse. So, basically you can see that the unit of the rate constant vary from zero order reaction to first order reaction to second order reaction. Okay. So, in case of this zero order reaction, the unit is concentration per unit time. So, the unit for the rate constant is always will be this concentration per unit time, and in a higher order reaction obviously k will have different units, which I have just told. So, if we go ahead and see the integral form of zeroth order rate law. So, this so how to derive the integral form of zeroth order reference law? So, integration of the differential rate. So, we know that this is the general rate law equation. So, if we go for the integration of the different rate laws, it is a concentration as a function of time. So, we start with the general rate law equation. So, first we write the differential form of the rate law when n equal to 0, which we just saw in our last slide, that is rate is equal to k, or dA 0 by dt equal to k. Now, if we rearrange this thing, we will get dA equal to minus k dt. So, this is the differential form. Now, second, if we integrate the both sides of the equation from a 0 to a and from t 0 to t. So, basically in both sides we are taking the integration, and if we solve it, ultimately we will get these linear equation form. So, basically this is again a straight line, where basically concentration of A equal to concentration of A at 0 time minus kT. So, basically the integrated form of Ray's laws allows to find the population of reactant at any time after the start of the reaction. So, if we see the graphical representation of both the differential form as well as the integral form of zeroth order of rate law, we will see this. So, in case of zeroth order of rate law, if we see the differential the graphical representation of the differential law, we will see that the rate is basically constant. So, if we plot the rate versus time, we will see a slope of 0. We are seeing a constant k. However, in case of zero order integral law, if we plot the concentration of A versus time, we will see a straight line which is having a negative slope. As you can see here, it is having this k is having a negative slope. The slope is minus a k. So, this is the graphical representation of the zeroth order of rate law. Now, you have see each of these zeroth order reaction as well as first order reaction and second order reaction can be expressed in terms of graph, and these graphs, when we plot them, they will identify whether it is a zero order reaction or first order reaction or second order reaction. Now, you may be confused that in case of first order reaction also, you have seen that there is a straight line with a negative slope. So, how you can differentiate the graph of a first order reaction to a graph of a zeroth order reaction? We will discuss that in details in coming slides. Now, to graphing a zero order reaction, we have already seen that the zero order reaction integral form can be expressed in terms of this equation, where we can express is in terms of y equal to m x plus b, that is the formula of a straight line, where m is equal to minus k, which is a slope, which is a negative slope, and y intercept b equal to a 0, that is concentration of a reactant at time 0. Now, zero order reaction are only applicable. You can see this is an integral representation, integral graphical representation of zero order rate law. Now, one thing is clear, that zero order reactions are only applicable for a very narrow region of time. So, the linear graph is only realistic over a limited time range. So, here you can see the time is basically in the x axis. So, this straight line will be valid only for a limited time range. So, if we were to extrapolate this line of this graph downward and to represent all values of a time for a given reaction, it would tell us that as the time progresses, the concentration of our reactant become negative. So, if we increase the time, and if you see the the concentration of a particular reactant, you will see that negative concentration, sometimes we achieve negative concentration, which is not possible. So, because concentration cannot be negative. So, that is why zero order reaction kinetics is applicable for describing a reaction for only brief window, because if we increase the window of time, then the concentration might reach negative, which is not possible. So, the zero order reaction kinetics is applicable for describing a reaction rate for only a brief window of time, and must eventually transition into kinetics of a different order. So, you will see that eventually as time progresses, this zero order reaction, which is basically a very transient one, will be converted to other order reactions like first order reaction or second order reactions. So, to understand where the above this graph is basically comes from, let us consider a catalyzed reaction. Okay. So, at the beginning of the reaction and for small value of time, the rate of reaction is constant. We know that from its differential representation, the rate of reaction is constant in case of zero order reaction. Now, and this is indicated by blue line of the figure. So, basically the integral form shows that it is a constant. As we increase, the concentration will go down, and if we plot the rate versus time, it will be a constant line. Okay. So, this blue line basically indicates that. Okay. Now, this situation typically happens, this situation basically happens when a catalyst is saturated with the reactants. So, when the catalyst active sites are already saturated with the reactants, then this kind of situation may arise. Now, with respect to Michaelis-Menten kinetics, you have already know what is Michaelis-Menten kinetics. Now, this point of catalysis or catalyst saturation is basically related to the maximum velocity, that is V max. Now, as a reaction progresses through time, however, it is possible that less and less substrate will bound to the catalyst. So, initially the catalyst site is saturated with the reactants. However, as the time progresses, the catalyst the site is less and less saturated or less and less occupied by the substrate. Now, as this occurs, the reaction slows and we see a tailing of the graph. Now, you can see as the time progresses, there is a tailing of the graph, as is denoted by this dotted line. Okay. And this portion of the reaction is basically represented by this dotted black line. Now, in looking at this particular reaction, we can see that the reaction is not the zero order under all conditions, they are only zero order in limited amount of time. So, that basically says that this reaction is following the zero order law for a brief period of time up to this, and after this it is following is some other order of reaction. So, here you can see the tailing of the graph has been started. So, that is why the zero order reaction is very transient one, it is actually it is actually applicable for very short window of time. So, if we plot the rate as a function of a time, we obtain this graph. We know that it is basically a straight line. Again, the only describes a narrow region of time. Obviously, the time will be very narrow region, and the graph is equal to k, which is the constant, rate constant. So, therefore, the k is constant with time. In addition, we can see that the reaction rate is completely independent of how much reactant you put in. So, it does not matter whether you put much amount of different reactants, the rate constant, the rate will be very much constant. And so, this is the zero order reaction. Now, you can see the differences between zero order reaction, first order reaction and second order reaction. So, how to determine in case of soil? Now, how to determine the reaction order and rate constant as far as the soil chemical processes are concerned. Now, there are three basic ways to determine the rate laws and rate constant according to the scientists. First of all, using the initial rates. Secondly, directly using the integrated equation and graphing the data, and third is using nonlinear least square analysis. Now, the second point, using the integrated equation and graphing the data, we have already discussed for zero order, first order and second order. Let us discuss what is the use of initial rate and how to use nonlinear least square analysis. So, before that, let us assume an elementary reaction where there are two species of reactants, species A and species B. So, there are two reactants, reactant A and reactant B, which are basically reacting to form the product Y. Now, here one thing you see that there is a forward reaction as well as there is a backward reaction. So, it is basically a reversible reaction. So, these are in equilibrium. Now, we can see here the K1 here, it is basically a forward rate constant, whereas for the reverse reaction this K minus 1 is the rate constant of the reverse reaction. So, this is basically equation 4. So, let us see what is the implication of this for deducing different types of order of reactions. So, if first order reaction rate law can be written from this previous equation, we can see dA by dt equal to minus K1 into concentration of concentration of AN product with concentration of B, where K1 is basically the forward rate constant and alpha and beta here are assumed to be 1. Now, you know alpha and beta are basically partial order of A and B. Now, the reverse reaction which we are talking about is basically dA by dt. So, here you can see it is positive. So, because it is in the reverse reaction, basically there is a generation of the reactant. So, here you can see this is basically positive, here it is the reverse rate constant and this is the concentration of Y, which is actually the product in the forward rate reaction. And in the reverse rate reaction or reverse reaction, this Y becomes the main reactant. So, here equation 5 and 6 are only applicable far from equilibrium, where back or reverse reactions are insignificant. So, basically this equation 5 and 6 can be only applicable when these reverse reactions are insignificant, which is so when there is a perfect equilibrium, the reverse rate is equal to the forward rate. However, when there is not equilibrium, then we are assuming that forward rate constant or forward reaction is more predominant. So, if both these reactions are occurring, then equation 5 and 6 must be combined. So, to get the net reaction rate, which is basically denoted by d and dt, it is basically summation of the forward reaction rate plus the backward reaction rate or reverse reaction rate. So, you can see the net reaction rate is the difference between the sum of all reverse reaction rates, we know that, and the sum of all forward reaction rates. So, basically if we arrange this, it will be just like d A dt k minus 1 y minus K A dot product P. So, this basically is satisfied. So, this is the net reaction rate, and this net reaction is the difference between the sum of all reverse reaction rates and sum of all forward reaction rates. So, this is how we can calculate the net reaction rate for any particular reaction where there is both forward reaction as well as backward reactions. Okay. Now, what is the initial rate? How we can use the initial rate? One way to ensure that back reactions are not important is to measure the initial rate. So, if we just nullify the back or reverse reaction and we only focus on the forward reaction, then we have to measure the initial rates. Now, initial rate is the limit of the reaction rate as time reaches the 0. So, obviously, at time reaches 0, that initial point, there is a higher concentration of the reactants. So, there is low concentration of the product. So, obviously, there will be less reverse reaction. So, with an initial rate method, one plot the concentration of a reactant or product over a short reaction period, during which the concentration of the reactant changes so little that the instantaneous rate is hardly affected. So, if we just concentrate on the instantaneous rate, in the initial rate method, then it is so little that the rate is hardly affected. So, thus by measuring the initial rate, one could assume only the forward reaction rates predominate. So, basically while we are talking about the initial rate, we are basically nullifying the reverse reaction rate and we are only focusing on the forward reaction rate in the equation 4. So, in the equation 4, we have seen there are two equations, one is forward equation, one is a forward reaction, another is backward reaction or reverse reaction. However, in case of measuring the initial rate, we are nullifying the reverse we are nullifying the reverse reaction. Now, this would simplify the rate law that given in equation 5. We have seen in the equation 5 that dA by dt equal to minus K1 into multiplication of concentration of A reactant and concentration of B reactant, okay, which is basically showing a second order reaction, right. Now, we know in case of second order reaction, the rate is basically proportional to the product of both the reactants concentration. So, this is how we can see it is basically a second order reaction, it is following a second order reaction. So, the forward rate constant is following a second order reaction in case of two different reactants. Now, equation 4 under this condition would represent basically a second order elementary reaction. Now, to measure the initial rates, one must have available techniques that can measure rapid reaction such as relaxation methods and an accurate analytical system method. So, we will talk about the relaxation method in our coming slides. So, these methods are very useful for measuring the concentration changes with a very short period of time. So, these methods are required for measuring this initial rate. So, just one example of how we can use the initial rate. So, if a reaction is the first order, as you can see in this plot. So, a plot of logarithm of AT and and versus T. So, if we plot the time in the x axis and logarithm of a concentration at particular time in y axis, then it will result in a straight line. We know that with a negative slope with a slope of k1 by 2.303. Now, why this 2.303 basically comes? So, if we convert to natural logarithms to logarithm, then we will get this value of 2.303. So, basically we are taking that into consideration. Now, this example of this first order plot for manganese sorption on this manganese oxide at two initial manganese concentration, at one is at 25 micromolar, another is 40 micromolar we are seeing here. So, basically we are seeing the sorption, how this manganese concentration changes as time progresses onto the manganese dioxide, then we get these two types of plots which basically showing the first order sorption process or first order reaction. Now, the Mn20 values or the initial Mn2 values obtained from the intercept of this figure basically are 24 and 41 micrometer, which is in very good agreement with the two Mn20 values which we have assumed, that is one is 25, another is 40. So, basically these reactions satisfy our condition. Now, the rate constants are 3.73 10 to the power minus 3 and 3.75 10 to the power minus 3 per second at Mn0 of 25 and 40 micromolar concentration. So, you can see this is the first order reaction. So, obviously, the unit will be per second. Now, the rate constants are not significantly changed with concentration. You can see here the rate constants are not significantly changed with concentration. So, this is how we can apply the initial rate to calculate to basically see which which order of reaction is basically following for a particular chemical process. Now, integrated equation. Now, integrated equation we have discussed in details. For the first order reaction, what should be the initial integrated equation, for the second order reaction, for the zeroth order reaction, what should be the integrated equation we have discussed, and also we have discussed the half life, we have calculated the half life for this. So, this is also very self explanatory how we can use these integrated equations basically to plot them and see how we can use, by plotting these integrated equation, we can see the straight line for both first order reaction and second order reaction, as well as for a transient time for a zeroth order reaction. So, by seeing the shape of these curves, we can identify which type of reaction order it is basically following. The third one is the least square analysis. Now, the least square analysis can also be used to determine the rate constant. Now, you know that with this method one feeds the best straight line to a set of points linearly related as y equal to mx plus b. So, basically if we just plot two sets of data, for example, let us plot x and y. So, if you plot two sets of data for different values of x and y and then draw a straight line, this straight line will be represented by a formula equal to y equal to mx plus b. Now, here the slope is m, whereas this b is basically the intercept. Okay. Now, how to calculate this line is basically a least square method. So, the least square method says that we will draw this line so that the residual or the summation of the residual or error terms will be least for this line as compared to any other line. So, although we can draw several lines to connect these points, the most optimum line will be drawn by the least square estimate. So, that is why any linear regression will be a simple linear regression or multiple linear regression is known as the least square regression, ordinary least square regression. Now, one thing is clear that this least square estimate, this using this formula, there are you can calculate the slope as well as the intercept b. Okay, can be calculated using the least square analysis. For example, in case of m, you can calculate by using this formula. In case of b, you can use this formula to calculate the intercept. Okay. So, this is the basically calculation based on the least square analysis, where n is the number of data points and the summation are all data points in the data set. So, basically it is basically drawing a straight line from a sample of or set of points where you have both x and y. You have predicted as well as you have the target variable. So, basically it is calculating the slope based on the data as well as calculating the intercept and then drawing the line. So, this is how we use the least square estimate. Now, curvature implication. Now, these curves which we have seen in case of first order reaction, zero order reaction, second order reaction, you will see sometimes there are some curvatures or aberrations. So, these curvatures may result when the kinetic data are plotted. So, these aberrations or curvature may be due to an incorrect assumptions of reaction order. For example, in case of first order kinetics, the reaction, if we assume the first order kinetics and the reaction is really a second order, then you will see a downward curvature. Now, secondly, if the second order kinetics is assumed, but the reaction is really first order, then you will see upward curvature. Now, curvature can also be due to the fractional third or higher mixed reaction order, and non-attainment of equilibrium often results in downward curvature. And also remember that temperature changes during the study can also cause curvature. So, guys, you have understand what is, in this lecture you have understand what is a zero order reaction, how you can plot the differential form of a zero order reaction, what are the condition of the zero order reaction, and what is the integral form of zero order reaction, how you can plot the zero order reaction, what are the methods, three methods, initial rate integrated form as well as least square method for identifying the order of the reaction in the soil we have discussed. So, in the last lecture we will be discussing about several important soil chemical processes in which the chemical kinetics are very important. So, let us meet in the next lecture and the last lecture of week 6 to discuss the practical implication of these order reaction in defining different soil chemical processes. Thank you very much.